So this lesson we've already previewed in a previous lesson. In topic 2.9, we talked about semi-log plots, and we learned how to read them, how to plot the coordinates, and why they might be helpful when looking at logarithmic functions. But there's actually a whole lot more with semi-log plots we can do. Remember, semi-log plots are the ones that, and there's one down here. They look like this. Do you remember seeing these? Where they're not an x and a y that are linear. The x-axis counts by like ones or something linear, counts by twos, counts by fives. But the y-axis is a log scale, which means every line represents a power of 10. So the big dash line is 10, and this is 10 to the 1, this is 10 to the 2, this is 10 to the 3, and every line in between it is like a unit within that. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, but then 20, 30, 40, 50, 60, then 200, 300, 400, 500, okay? That is what we're talking about, is the log scale. So why are they important? Why do we want to do them? In a semi-log plot, one of the axes is logarithmically scaled. For AP Pre-Cal, we will only be scaling the vertical axis. In real life, you can also scale the x-axis, and that's called a log plot when both of them are log. But we're only doing semi-log, so one of them is logged, which is the y value. And with a semi-log plot where the y-axis is logarithmically scaled, exponential functions will appear linear. That's huge. We're going to highlight that. That's a huge concept for today. In fact, we're going to rewrite it in our own handwriting on here because it's so important. We're going to write down that exponential functions are linear on semi-logs. So if you're looking at a semi-log plot and you see a linear equation, a straight line, you are actually looking at an exponential equation. So exponentials are linear on logs. Whoa, exponentials are linear on logs. So if we look at an example, and this is the same example from the 2.9 notes displaying the population growth of English Americans in the United States from 1620 to 1820. Obviously, it looks like nobody lived here right away because it's so small, and then all of a sudden the population grows really big. But if we log scale this information, we can actually see what's happening in those early years, that there was about, 500 people that came over on the Mayflower, and then our population started to become linear after a few years. So yes, it's not perfect because it's real life data, but do you notice how this is essentially a straight line? It's linear on a logarithmic graph, so it's actually representing exponential data, population growth. So example 1 says, use the features of the semi-log plot to justify why an exponential model is appropriate for the population of English Americans in the current United States from 1620 to 1820. So exactly what we said before, we would write in words, and yes, it's a writing example. We would say the semi-log plot semi-log plot above appears to be linear after approximately 40 years. So looking at that, bless you, starting at 1660, bless you again. So the exponential model is appropriate. So what I'm talking about again is how on essentially from here on it models linearly. So this is a good model for this data, to look at it logarithmically, to look at it on a log scale, because it's essentially linear, so we get a lot of information about the exponential itself in this log scale. Exponentials appear linear on semi-logs. That is the huge takeaway from this. So we look at that second example. Didn't stick. We look at that second example. It says, after Mr. Passwater tells another one of his hilarious math jokes, it begins to spread around the school. The number of people that have heard the joke after T minutes is graphed on the semi-log plot above, where the vertical axis has been logarithmically scaled. Which of the following functions could be a model for P? Okay. What do you notice about this graph? Number 1, it's a semi-log plot. Number 2, what is happening to the data? It's linear. So we're pretty sure, since we can see this linear data here, we're pretty sure that the answer choice that we should pick should be some sort of, so we can see since it's linear on a log, we're looking for an exponential answer. Which 2 answer choices here can we for sure get rid of? Which ones are not exponential? A and C are not exponential. In fact, what kind of function is A? Linear. What kind of function is C? Logarithmic. We're looking for an exponential function, so either B or D is correct. Now, if we think about what we learned from exponential functions, we know a good amount of information. We know that the A value, which is in front of the base term in an exponential, so what I'm talking about is this format right here. The A value is your y-intercept. It is your initial value. So based on this graph, what is my initial value for this function? 2. That's right here. That's my initial value of 2. The B value tells you your growth or decay factor, so how it's growing or decaying. If you're looking at essentially these numbers, and we're going to put them into a graph since these are our notes. If we had the minutes on this side and then the people on this side, and we started reading this graph, you guys saw that at 0 minutes, 2 people had heard the joke. How many people at 1 minute had heard the joke, approximately? 4. At 2 minutes, approximately how many people had heard the joke? You can make a pretty good guess that it's going to be 8. Guess what happens at 3 minutes? 16. So what's happening to the number of people who hear this joke every time? It's doubling. So which answer choice, B or D, tells me I have a y-intercept at 2 and it doubles every time? D is correct. That is a y-intercept of 2, bless you, and it doubles every time. Part B does double every time, but it has a y-intercept of 1, and it is translated up 2 units, which is different. That means we would be starting at 3, because we start at 1 but move it up 2, because that's a vertical translation. So we can still tell a lot about functions when it's in this log scale or semi-log plot. Yes? Yeah. Okay. So some important information about semi-log plots. When we logarithmically scale the vertical axis for a semi-log plot, we are not changing the y values. I know it looks like it because we're plotting them at different numbers. We're not changing the y values. We are actually equally spacing the y-axis proportionally so that the output values are the same. The x-axis should always be linear. The y-axis should be proportional or multiplied by some value to be a log scale. Let's highlight that for a second. So our x values are linear and our y-axis is proportional. Remember, proportional is the word that we use to talk about multiplying in either a geometric sequence or in our exponentials and logarithms. So in example 3, it says the table above gives selected values for function f. Which of the following graphs could represent this data in a semi-log plot where the vertical axis is logarithmically scaled? We've got 4 options here for which one it could be. The way we make sure we know it is a semi-log plot is we look at the x and y axis. So looking at the x-axis here, is this one linear? Are we counting by a single number every time, like counting by 1s or counting by 2s or counting by 3s, something like that? No, this one actually has been logarithmically scaled. We don't want that. We'd already eliminate this answer choice, but these are your notes. We're going to look at it a little bit more. What's happening on the y-axis here? You see how and I'm not talking every single line, but every thick line is 0.5 and then 1 and then 1.5. That's going up by the same number each time. That's linear. This is like the opposite of what we want. We want the y-axis to be logarithmically scaled instead of the x-axis. So we're going to eliminate that one. It's not even set up right. Let's look at answer choice B. For the x-axis, is it linear or logarithmic? Linear. For the y-axis, is it linear or logarithmic? Are those equally spaced or are they proportionally spaced? They're proportionally spaced. That's a logarithm scale. It only goes from 1 to 10, but it's still a logarithm scale. So they're not equally spaced out. We're going to keep that one because that's set up correctly. We look at answer choice C. What is the x-axis? Linear. What is the y-axis? Also linear. Okay, that's wrong. We don't want that. Linear and linear is what we've done since like 3rd grade when we started plotting points. For answer choice D, what is the x-axis scaled by? It's linear. Okay, good start. What is the y-axis scaled by? That one's logarithmically scaled. Okay, cool. So we have 2 options for which one this could be. Now, we need to just make sure we pick the appropriate graph. So if I actually look at the points I'm trying to plot, I want to plot 1, 40. Which one of these graphs actually did plot 1, 40 correctly? D. Yeah, this is actually 1, 40. The other one is just like plotting random points somewhere. So we choose answer choice D. We do also want to make sure that when we're choosing these plots and we know the data is exponential, which we can tell in the table, that we do have a linear equation showing up on my log scale. I know that this is exponential because these values are growing faster and these are growing linearly. So there's a linear on the x, proportional on the y. All right, example 4, we've already done a problem like this before on our 2.9 notes. We're just gonna make sure we can plot these points because it's a huge help to selecting the correct graph, like maybe on your next test that you pick the right points, is knowing where they were plotted on this semi-log plot. So let's plot A together. On your graph, we would go to an x value of 0 and a y value of 200. So I'd go 1 step above 100 because it's 1/100 more than that. So this is answer choice A, or sorry, coordinate A. To graph 1, 25, we'd go to an x value of 1 and a logarithmically scaled y value of 25. So if this is 10, that means this is 20 and this is 30. So in between them is going to be 25. This is B. Can you guys finish the rest for me? Okay. To plot 2, 7, we'd go to an x value of 2 and a y value of 7. So if I was trying to be super precise here, this is 1. So this is 2, 3, 4, 5, 6, 7. Yes, it gets a little crowded in there, but 2, 7 would be 1, 2, 3, 4, 5, 6, 7. Would be right there. That's C. 3.2, 800. Well, if I look at my x-axis, I have 5 tick marks between 3 and 4, which means obviously to get there is a base 10, so every tick mark is 0.2. So I'm going from this x value of 3.2 up to 800. So that's going to be 100, 200, 300, 400, 500, 600, 700, 800 up in there. It's, again, really small, but you can get it. 1, 2, 3, 4, 5, 6, 7, 8. That's D. And last but not least, coordinate E is at 4.6, 1.5. Again, every tick mark on my x-axis is 0.2. So this is 4.2, 4.4, 4.6, and then 1.5 is just going to be a little smidgen above it. Because your bottom line is not 0, your bottom line is 1. So that's E right there. Did we remember how to do this? Okay, we were really good at this the first time I showed it to you, so that's cool. That's cool. So semi-log plots, not hard to read, easy to see that it comes from exponential data. What's difficult about semi-log plots is what we're doing on the next page. And I'm going to slow down when I talk about it because it's actually new to me. I had never done this before teaching this class this year, so I need to make sure I'm explaining it to you correctly. So as we have seen, if we graph an exponential function on a semi-log plot, the graph will appear linear. We said this earlier that all exponentials are linear on semi-logs. Since it's linear, we can actually write a y equals to mx plus b equation for this. That's a linear parent function. They're just going to be not m and b, they're going to be different coefficients, different constants. So given an exponential model, y equal to a times b to the x, the corresponding linear model for the semilog plot is given by y equal to log sub n of b times x plus log sub n of a. Whoa, where'd everything come from? Let's talk about it. In your exponential model, you have a. That a still tracks over here. In your exponential model, you have b. That b tracks over here. Those letters have stayed the same. That's where we're getting the a and b from. The n corresponds to the base used for the scaling of the vertical axis. That's down here. The base n corresponds to the base used for the scaling of the vertical axis. That's where we're going to get this number from. Now for a semilog plot that we're doing, we have seen base 10 every time. So for a lot of the problems you're going to see in this class, that n value will be 10, so we are dealing with a common logarithm. Obviously, it's not always the case, but I think for this class, we can guarantee that we're going to see base 10. Could be wrong. Like I said, it's first year of teaching this class ever, so we'll get more information as we go. But if we notice, the slope of our linear equation is always in front of the x value. So this term right here is our slope, is our m. And our y-intercept, which is always by itself in a linear equation, is added at the end. I'm not going to write y equals mx plus b on here because we've used a b already. But what we can do is remind ourselves that this is y equal to the slope times x plus the y-intercept. I don't want to use m and b again because b we've already used as a letter and it would just confuse you. But if you look at it, this is just a y equals mx plus b equation. The m and the b just come from a logarithmic expression. So our slope is log base n of b, and our y-intercept is log base n of a. Our last example of today says the semilog plot above corresponds to the data table from example 3. So these are it's a table. If you flip back on your notes, we had a table of values that we were looking at. We want to write an equation for the linear model for the semilog plot of the form y equals to log base n of b times x plus log base n of a. This one is a little bit confusing, so just stick with me. So we want to write a linear model for the semilog plot data. We are trying to write the equation of the line that passes through all of these points. When you are writing an equation of a linear line, you need a slope and you need a y-intercept. We don't have either given to us in this problem because we are not given the number for the value of 0, of y sub, when x is 0. So we have to find both of those things. To find the slope of this line, we're going to use the formula for average rate of change, which y'all keep forgetting on me and you need to know for your test. So let's write it down, why shall we? So if we're finding the slope of this line, that's the same thing as finding the average rate of change between two values, because slope and average rate of change are the same things. When we're finding slope, we're finding average rate of change. We're going to find the function value at some second x value minus the function value at some first x value divided by the second x minus the first. That is y2 minus y1 over x2 minus x1. It's the same slope formula you've used since you started doing algebra. It just looks fancier because we're doing it not with just plain points, but with an average rate of change. That's not on a linear function. So we can read our graph to find these things. Let's let x2 be the value 2 and x1 be the value 1. So I am looking at this x value and this x value. I want the output at those two inputs. What is the output when the x value is 1? What value is that on my graph? 40. So we're not just going to put 40 though, because this is log scaled. So we're going to say log of 40. Okay. What about the value 2? 60. So in my average rate of change formula, I'm going to say log of 60. That is all numbers. So let's turn to our calculator, and with a fancy fraction maybe, do log of 60 minus log of 40 over 2 minus 1. So you get some decimal value, yeah? You should get approximately 0.176. Before you lose this in your calculator, I want you to store it as m. Why m? Because it's my slope, and we think about slope as the value m. Cool? We found the slope. We just now need the y-intercept. The problem is I can't read the graph to find the y-intercept because I just drew this line willy-nilly, and we need an actual value for it, so we're going to use algebra to solve it. So we know that this equation is going to be y equal to my stored value m times x plus log of a. Let's plug in some input and output values. Okay, sorry. We're going to solve this equation for log of a, because that's what we're trying to find. We're trying to find b. So if we solve this for log of a, we would say log of a is going to be equal to an output minus my saved value m times x, right? I just subtracted m times x to the other side of the equation. Do we follow? We need to input values for x and y so we can solve for this log of a. Based on the graph that you guys told me, log of a can be equal to an output of log of 60 minus my m times the input value of 2. Because we had the coordinate point 2, 60 from my graph. So it's an input and an output. Change the color code on this. At this point, everything that log of a is equal to is a number. You saved m in your graph or in your calculator already. So now go to your calculator and you say log of 60 minus m times 2 or 2m. What did you guys get when you found log of a? Should be 1.426, no? Yeah. Okay. Now again, we just had to round that number, so we're going to store it in our calculator. Since we're solving a, what is happening on my screen here? Since we are solving a linear equation, y equals mx plus b, we're going to go ahead and save this value as b. And that might be confusing because it's not the same b from our logarithm version, but I think our brains can handle that. So to finally answer this question, and I've run out of room, so I'm going to come up here to the side to do it. It says, write an equation for the linear model for the semilog plot of the form y equals mx plus b. We've done that. Our equation is y equal to 0.176 times x plus 1.426. Okay, I know that was a little disjointed because I did not do the best explanation of my life. So are there any questions? Let me rephrase. What are your questions about this process, about what I did? I know you have them. So walking back through it again. To find the m is your slope. Slope is an average rate of change. We needed an output and an input pair to find slope, which is the same thing we've been doing about slope since forever. You needed an x1, y1, x2, y2. That's what I've done here. To find my slope, which is the average rate of change, I found an output and an input for two separate values. Based on the graph, we got these numbers. At 1, the output is 40. At 2, the output is 60. So when I find the average rate of change between those 2 points, since it's log scaled, I have to put the log here so I find the actual value of the actual points of the exponential equation. And we get our slope. Now if you're like, Ms. Quigley, that doesn't say m, how is that slope? Remember, this log base n of b is in the spot of slope in my equation. So finding log of b is finding my slope. Those are the same things. Did I pass your question already? Okay. Once I have m and I've stored it in my calculator, I can plug it back into the equation and do some algebra to find the missing term. Now, I rearranged the equation before I plugged stuff in, which is maybe where I lost you. This is the regular equation, substituted the purple for m. Yes? Bless you. All I've done in this step to this step was solve for log of a, which was getting rid of this m times x by moving it to the other side. So we have log of a equal to y minus m of x. At this point, I'm just solving for the y-intercept. I just did it with algebra instead of plugging in numbers. But once I plug in numbers, I just need an input and an output pair from the graph to solve for log of a, which is 2, 60. At this point, all of this is numbers because you have m stored in your calculator. So log of a, which is representing my y-intercept, is approximately equal to 1.426, which is what we get when we type this in. So we have our slope, and we have our y-intercept, which we put in the linear equation itself. Yes?
So we can use the log of 40 minus m minus, or m times 1, 2, instead of just like the log of 60?
Yes, you're talking here. You could have plugged in 1 and log of 40, yes. You could have plugged in any of the points along the line. I just picked that one because that happened to be what I did when I worked the problem on my piece of paper. You could have picked any of the coordinate points along that line. Because it's a linear equation, it should stay consistent the whole time. That's a good question. Anything else on this? And of course, we're not done yet because we've written a linear equation, but since this is a linear equation on a semi-log plot, we know it actually represents an exponential function. So we have to take this linear equation we just wrote. By the way, did you store the value for m and b in your calculator? Yes. Don't forget to store b. We're going to need that. Always store your values when you round, especially if there's a part b of your question, because now we're going to use the linear model we found in part A to write the equation of the exponential model, a times b to the x, for the same data. But here's what we know. We know that the value we have solved for m is exactly equal to log base 10 of b. I know it's base 10 because that's logarithmically scaled by 10s on the side of this graph. So n is 10, so I can just write it as a common logarithm. Do we see where I put the m, why the two purple things are equal to each other? They're in the same spot of the equation. How do I solve for b here? If it's inside a logarithm and I want it out, what do I do? The loop. So what's the base here? 10. If we take 10 and raise it to the m power, that should be equal to b. You still have m saved in your calculator. So right now, do 10 to the m power and tell me what b is equal to. 1.5. Actually, that doesn't even need the squiggly lines. That's an equal to 1.5. That's nice. We like that. We're going to keep that. We're going to do the same thing for the A value. So we found B, now we need to do this with A. So my B value that I've saved in my calculator is equal to log base n, which is 10, of A. So again, how do I solve for A? Log loop. So this is going to be 10 raised to that B value that we saved equal to A. And when you calculate this, you should get a repeating decimal. 26.6 repeated, yeah? Does anyone know that when you have 0.6 repeated, it's divided by 3? When you have 0.3 repeated or 0.6 repeated, it's something divided by 3. That's going to be a pretty fraction. So right now in your calculator, press math fract. Make that a cute fraction for me. Did you get a cute fraction? I mean, it's an improper fraction, but it's like pleasant. You should get 80 over 3. Is that what you get? I don't even need the squiggly line equations anymore when I have that fraction because it doesn't lose any specificity. If I answered with 26.667, I would have had to use the squiggly lines because that's a decimal approximation. So if we're actually writing the equation here, we have y equal to 80 divided by 3 multiplied by 1.5 raised to the x power. You just put A where A goes and B where B goes. Woo-wee! Cool, right? Yeah, so cool, Miss Quigley. I know. Incredible. Semi-log plots are something that are really cool because they're, again, something that's used in real life. A lot of engineers plot their data on log plots. So if you're planning on being an engineer, you will see this again when you look at data in your future.